course BSc Bachelor of Science undergraduate courses. Subject nuclear physics. Topic is binding energy, in which I will discuss the basic concept of the binding energy and related problem, and then after a comparison with the packing fraction. How both are complement to each other. Right. This is part number 5 of this video lecture series. If you are interested, you can like my Facebook page www.facebook.com/apniphysics, and for such video lectures you can visit www.apniphysics.com. Myself, Dr. Sushil Kumar. Today topic of discussion is binding energy. Right, simply we write it binding energy, and then after we will discuss about the binding energy per nucleon and related numerical problems. So what is the binding energy? In the earlier lectures we have seen the basic concept of the mass defect and the packing fraction. Now the concept of the binding energy, which is directly depends on the both concept, mass defect as well as the packing fraction. How this binding energy can be explained on the basis of that packing fraction or mass defect, that is the purpose, and how it is useful to explain the basic properties of the nucleus, because binding energy one of the important parameter into the nuclear physics to understand the not only nuclear forces but also structure. So the simple definition of the binding energy, that is equivalent to the mass defect, is called the binding energy of the nucleus. Right. It can be defined as the energy which is required to separate a nucleus into its constituents particles, neutron and proton. Right. The mass defect you have seen, this is the Z proton number, mass of the one proton, total neutron number and mass of the neutron in atomic mass unit. If we take the sum of these two constituents particles into the particular nucleus and subtract the actual nuclear mass, we get the information about the mass defect. If we multiply this mass defect with the c square, we get the Einstein mass energy equivalence relationship, delta E is equal to delta mc square, where delta m is the mass defect. So binding energy is defined with the simple formula delta mc square, where you have seen that we just multiply it with the c square, and right now this is in atomic mass unit. In earlier lecture you have seen that one atomic mass unit is equal to 931.5 mega electron volt. Right, so this is the basic idea of the binding energy. Here a simplest case of the deuteron is considered, which we had already taken as an example for the mass defect. So this is simple hydrogen atom, and mass of the hydrogen, that is mass equivalent to the mass of proton, is equal 1.007825 atomic mass unit, and mass of the neutron is 1.008665 atomic mass unit. If we add these two, one proton and one neutron mass, we get this 2.016490 AMU atomic mass unit. And in general the deuterium mass is equal to 2.014102 AMU. So the binding energy is equal to delta mc square, that is basically this difference into the mass 0.002388. This difference came through this actual mass of the deuterium and sum of the masses of the constituents. Deuterium has only one neutron and one proton. So this difference delta m is the mass defect. If we multiply it with the 931.5, we will get this 2.224 mega electron volt, and this is the binding energy of the deuterium. The energy equivalent of the missing mass is called the binding energy. Actually, what happens here, you are observing carefully and you have also a basic idea of the binding energy. Here the total mass is more as compared to the major mass. So where this mass gone, missing mass, basically that mass is used to bind those nucleons, and that is defined in terms of the binding energy. Mass defect basically define the binding energy. The missing mass, one can in a simple language, that is used to bind the nuclear system. So here if we want, suppose break this deuterium nucleus, so we will require this 2.224 mega electron volt energy, right? So if we bombarded this gamma ray photon on this particular nucleus, it will break into the proton and neutron. So the binding energy of the deuterium nucleus is 2.224 mega electron volt. A gamma ray whose energy is the same or more can split the deuterium nucleus into its constituents, which are proton and one neutron. Right, a gamma ray whose energy is less than 2.224 mega electron volt cannot do this. So by this way one can understand the idea of mass defect binding energy. So here binding energy per nucleon concept, the amount of energy which is required to release a nucleon from the nucleus is called the binding energy per nucleon. So this is simply can be defined binding energy divided by mass number, and this is mass defect here, Z multiplied by the mass of the proton and mass of the neutron, and this is mass of the nucleus multiplied by C square divided by A, right? And at the end you can multiply it with 931.5 mega electron volt, right? So this is the binding energy per nucleon concept, and here you can see that the behavior of various nuclei with the mass number A. When we increase the mass number, then how the binding energy per nucleon behave, right? So here this is the light mass region, and we are increasing the mass number. So this is the behavior initially for the light nuclei. You can see some kinks up, some kinks down, and here the maximum height of this binding energy per nucleon curve, and then after it starts to decreasing, and you up to this point, or you can say that it remains almost constant in this particular region. There is no large variation. So on the basis of this particular binding energy per nucleon curve, we can conclude some basic points of the nuclear physics. So here the one point is about the fusion and second point is about the fission. So in the lighter mass region, here these two lighter nuclei, when fused together, they form a heavy nucleus and some energy release. And similarly, when a heavy nucleus breaks up into two smaller parts, and some energy also released in this process. Now the points related to the binding energy per nucleon. Iron is the most stable element. Here 56 iron have 8.8 mega electron volt per nucleon binding energy. It means if one have to remove one neutron or one proton from the 56 iron, we will require 8.8 mega electron volt energy per nucleon. A large amount of energy is released by fusion of light elements into heavier elements, or by fission of heavy elements into lighter elements. Binding energy per nucleon of deuterium, you have seen that is approximately to 2.2 mega electron volt, and now divide it by 2, so you will get 1.1 mega electron volt in case of 209 bismuth. Total binding energy is 1640 mega electron volt divided by A, that is mass at mass number, then it is 7.8 mega electron volt per nucleon. So here 1.1 mega electron volt per nucleon is the binding energy per nucleon for the deuterium. Here 7.8 mega electron volt per nucleon. Right, so binding energy of all stable nuclei are positive. Peaks in binding energy at A is equal to 4, and for light nuclei in the medium mass region, the binding energy per nucleon remains almost constant. You can see here in this particular region, this binding energy per nucleon curve is constant. These are given in some numerical problem also, but as a point, if we can somehow split a heavy nucleus into two medium sized one, each of the new nuclei will have more binding energy per nucleon than the original nucleus. The extra energy will be given off, and it can be a lot of amount. So we will discuss all these points in numerical problems. Let us take in a simple example, fission process. Here this is 235 uranium. When bombarded by the neutron, slow neutron with energy in order of an electron volt, what happens? This uranium breakups a compound nucleus form. Basically, first of all, U236 23692, right, after the bombarding of the slow neutrons, and as a result what happens, this compound nucleus basically is not in a stable configuration. It breakups into two parts. One is the 89 krypton, and second is the 1, and these neutrons, 3 neutrons emit from it with some energy. So this is the fission process. The next point, if we join two light nuclei together to give a single nucleus of medium size, it also means more binding energy per nucleon in the new nucleus. For example, if two deuterium nuclei combine to form a alpha helium alpha nucleus, over 23 mega electron volt energy is released. Such a process is called nuclear fusion. Nuclear fusion is the main source of energy in sun. So you can see the path. This is the for fusion, and this is path of the fission. So there is a one objective question. Which element has the highest binding energy per nucleon? Number 1, neon. Number 2, iron. Number 3, iodine. Yes, iron have the highest binding energy per nucleon. One more question, that is, where does the energy released in the nuclear reactions of the sun come from? Covalent bonds between atoms, binding energy of electrons to the nucleus, or binding energy of the nucleons? Yes, third one. In the earlier slides, we have seen the basic concept of the binding energy, mass defect and packing fraction. Here in this numerical problem, so to calculate the binding energy, first of all, what is the important parameter which we have calculated? That is the mass defect. So first of all, we have to calculate the mass defect, and for that we have to add the mass of the constituent particles. There are 26 proton and 30 neutrons. So first of all, 26 multiply by the mass of the one proton, that is 1.007825 AMU, plus how many neutrons are there? 30, and multiply each by the 1.008665 AMU. right? So this is the sum of masses of the constituents of that particular nucleus, and subtract, so the difference will be, so let us calculate it, and mass defect is equal to Z multiply by the mass of the proton and multiply by the mass of the neutron number. Just take the sum of these two and subtract this one, mass of the nucleus, that is given 55.934932, and when we simplify it we get this mass defect that is of the order of 0.528648 AMU. Now we have to convert it into the mega electron volt. For that we multiply it by 931.5 mega electron volt, and as a result this mass defect becomes the binding energy, that is equal to 492.003 708 mega electron volt. And now we have to divide it with the number mass number, which is 56 for the iron given, and as a result we will get this 8.785 mega electron volt energy, and this is the binding energy per nucleon. Here in this numerical problem we have to calculate the packing fraction of 16 oxygen nucleus. The mass of the proton and mass of the neutron we know, we will use it to calculate the binding energy per nucleon. So first of all we have to calculate the packing fraction. The formula of that is equal to mass of the nucleus MAZ and minus A, that is atomic mass number, divided by A. Here one thing is very important, that this we know A is equal to N plus Z. So A into 1 AMU is not equal to N plus Z into 1 AMU, right? So the value is totally different. So this point we have to keep remember. So don't put this value, right? So now the point is, we know MAZ, that is given 15.99. So I have to convert it into the mega electron volt, that is 14889, this value for the MAZ in terms of mega electron volt. A is 16, so 16 AMU is converted into mega electron volt, and that is 14904 mega electron volt. Now put this value here and simplify it, we get this result, minus 3 into 135 into 10 raised power minus 4 packing fraction, right? So this is one of the point. So, and second point, now if we have to calculate the binding energy of the 16 oxygen, then there are 8 protons and 8 neutrons. Mass of the one proton is 1.007825 in terms of atomic mass unit, and for the neutron this is 1.008665 atomic mass unit. Sum of this is equal to 16 point something, and when I convert it into the mega electron volt, the value is this one, 15026.88348 mega electron volt. Now the binding energy is what? Binding energy is the difference between the masses of the constituents and the nuclear mass. So constituents nuclear mass is equal to this one, and nuclear mass is this one. The difference is 127 point something, and when I calculate the binding energy per nucleon for the oxygen 16, this is 7.97 mega electron volt. So by this way one can calculate the numerical problems which are related to it. Now the second one, and the important point, relative strength of nuclei on the basis of binding energy per nucleon. For an example, the binding energy of nucleon for the deuteron is given, alpha particle is given, and 16 oxygen is also given. In case of deuteron, you have seen that is 1.1 mega electron volt per nucleon. Obvious, the comparative statement says that where the binding energy per nucleon is more, that system will be more stable as compared to the lower value. So deuteron is less stable as compared to the 16 oxygen. So 16 oxygen is more stable nucleus. Does binding energy per nucleon curve, you have seen it earlier, is complementary to the nature of the packing fraction? What are the relationship between these two curves? We have seen packing fraction curve, we have seen binding energy per nucleon curve. So does both are complement to each other? So let us analyze this particular concept. So delta M is equal to, which are defined here, mass of the nucleus minus A. So nuclear mass and atomic mass number, and if we multiply mass defect with the C square, we get the binding energy. So here this delta M is associated with that packing fraction concept. Delta E is equal to delta MC square, the difference between the masses of the constituents of the nucleus and the nuclear mass, that ZMP plus NMN minus MAZ. So this is the mass defect delta M with respect to the mass number. So we used this idea into the packing fraction, and here this difference into the masses we had used into the mass defect, right? So packing fraction is equal to MAZ, mass of the nucleus, minus difference if we divide it with the mass number. So this is the ratio of the deviation of the masses with respect to this atomic mass number to the atomic mass number. And binding energy per nucleon is the delta E upon A, where delta E is equal to delta MC square. Delta M is the mass defect, which is calculated by this way, right? So binding energy per nucleon. What was our concept? We are just looking any similarity between the binding energy per nucleon curve and packing fraction curve. Are they complement to each other? Yes or no? This is the point. Conceptually, both binding energy per nucleon and packing fraction are different. You know A is equal to N plus Z. Atomic mass number is equal to N neutron number plus Z proton number. And atomic mass number in terms of the mass can be written as A into 1 AMU. Second point, mass of the nucleons with A number, that will be Z into Mn plus Nmn AMU. So in this particular section of the video, I am just focusing on that the atomic mass of the nucleus and the mass of the constituents is totally different. By taking an example of the alpha particle, this 4 is the atomic mass number, 931.5 is 1 AMU. So if I multiply it this number, so I get this 3726 MeV. And if I see independently, because in alpha particle there are 2 proton and 2 neutron. Similarly for the 2 proton, that is this one, and sum of these 2 is equal to 3756.72087. So sum of the masses of the constituents of the nucleus, they are 2 and 2p, is equal to this one, and correspond to the atomic mass number, the value is equal to this one, 3726 MeV, and here this is 3756. So this is conceptual difference between this idea, right? How packing fraction is complement to the binding energy per nucleon. This is the main question, this is the main concept on which I have to discuss. So explanation of it Here I have considered that mass of the proton is equal to 1 plus Fh, and Mn, mass of the neutron, is equal to 1 plus Fn. You know that Mh, mass of the hydrogen atom, is equal to mass of the proton. So here Fh is equal to considered as a numerical value, that is 0.007825 AMU, and Fn is equal to this one, 0.008665 AMU, and both Fh and Fn are constants. Now the point here, we know that mass defect can be defined in terms of this formula. So the formula of mass defect is represented by this symbol EB, that is ZmH plus Nmn, masses of the constituents, and this MAZ is the mass of the nucleus. Here we had already defined MH and Mn. MH is equal to 1 plus Fh, and Mn is equal to 1 plus Fn. MAZ as it is. Now simplify it. I have simplified it here. Z plus ZFH plus N plus NFN minus this atomic mass nucleus as it is. So now I am keeping together this Z plus N, that is A, plus this ZFH and this. Now the point is related to this atomic mass nucleus, how I convert it into the packing fraction. So in terms of the packing fraction, let us see how. So you know that packing fraction is defined by this way: MAZ minus A upon A. A is equal to MAZ minus A, or further this can be written as A 1 plus F is equal to MAZ, right? So this MAZ is equal to A 1 plus F, so I can put this value MAZ into the as A 1 plus F. So N plus Z, ZFH plus NFN minus A 1 plus F instead of this MAZ. And now further simplify it. N plus Z is equal to A, and I am opening this bracket, so as a result minus A and this minus AF. A cancel out with this one, and rest of the terms are this one, ZFH plus NFN minus AF. Now further, F is equal to MAZ minus A upon A, you have seen it, and here MAZ up minus A is equal to delta M, right, which we had already defined. So F is equal to delta M upon A. So after simplify it, FA is equal to this delta M. So instead of this FA or AF, so now the next term AB is equal to ZFH plus NFN and this minus delta M. We know that FB is equal to EB upon A. So when I divide this equation, this particular equation with A, so this term together, ZFH plus NFN divided by A minus this delta M upon A, right? So what I found here, FB, that is equal to EB upon A. Here FB and EB are symbol. So FB is equal to ZFH plus NFN upon A minus F, that is the packing fraction, right? This delta M is what? This is MAZ minus A. So this becomes packing fraction. So this FB, which have the information of mass defect in terms of the binding energy, is equal to this particular factor, which is a constant. You know that Z is number, F is also number, N is number, Fn is also number, A is also number. So this is just only a number for the nucleus, but F is the packing fraction. So this FB gives the information of the binding energy mass defect depends on the F. So Fb depends only on F. So here this term is constant, and for lower mass region where n is equal, Fb is equal to Eb by A, that is correspond to the binding energy per nucleon, is equal to constant term minus packing fraction. I know the concept. What we are doing here, I am just remind to you in this flow that I am just trying to correlate between the packing fraction and the binding energy curve. How the nature basically binding energy per nucleon curve depends on the packing fraction. This is going on. So now from the formula, Fb increases when F decreases. F decreases if this value of the packing fraction is decreasing, so that time F will increase. F decreases, Fb, this value basically decreases when F increases. So both are vice versa. This simple statement one can see into the real picture of the packing fraction and binding energy per nucleon curve. So here this axis, y axis, is for the packing fraction, and on x axis the mass number is considered. This is the reference line at 0. Right below this all the values of packing fraction for any particular nucleus, right, that will be positive or negative. Positive upper side, negative lower side. So for the lower mass region, this is 0, 1, 2, 3, like this one, 16, 20, 40, 120, 240, like this. So here for the light mass region, the packing fraction is maximum, right, and as the mass number increases, the packing fraction at particular point of oxygen, it becomes 0, and then after it decreases for the intermediate mass region, and then after it is increasing further with the mass number. In general, we know that the negative packing fraction shows the stability of the nuclei, right, and positive packing fraction shows the instability into the nucleus. So now let us see into the binding energy per nucleon curve. This is y-axis at which we have considered the binding energy per nucleon. On x-axis we have considered the mass number. So for the light mass region, light mass nuclei, you see some kinks here, and the binding energy per nucleon curve increases, right, with the mass number. So initially this is very small, and then after it increases, and after, right, near about to the 8 mega electron volt. So here the value of Fb is minimum, and here is maximum. So initially for the light mass region, Fb is minimum, but here F packing fraction is maximum. Here you see this binding energy per nucleon value, which is hidden into the Fb symbol, is maximum, but here you can see the value is minimum. So this information you can see with this mathematical formula. Binding energy and packing fraction are complement to each other and gives the information about the nuclear stability. Thanks for watching this video. I understand this concept and complicated, and but if you had liked this lecture and information, please like and subscribe this video channel. So please like and subscribe if it was helpful to you. Thanks once again.